from Sci-Fi. So, go.
Thank you very much. Get my hat off. I'm indoors now, right? I don't have to protect myself from the sun. As he said, my name is Keith Packard. I work for Sci-Fi right now. Sci-Fi, as you may know, is a RISC-V semiconductor design house. I joined in the summertime, and I've had in summertime North America, in Northern Hemisphere, so in July. And I've been having a great time. I've been working on picolibc for about 1.5 years now. Started out as newlib nano, which turned out to be a name that was in use. And so I changed the name to picolibc. So I'm talking about embedded C libraries. This is not small Linux systems. This is not full-time. There's no operating system typically in an embedded system. On embedded C library, typical applications, so I'm thinking thermostats, refrigerators, that scale of system. A typical embedded C library application needs very little out of the actual library itself. It probably needs some math functions. I may do a couple of square roots, maybe a little trigonometry. You're going to need, oftentimes the mathematics functions are being executed on a processor that doesn't have a floating point system. So the math functions that you want need to be kind of cognizant of what soft float restrictions are and the performance characteristics of those. Oftentimes the only functions you end up using is string functions, strcpy, memcopy, memmove, and formatted printing or debugging. Typical deeply embedded system doesn't even use, doesn't have any file system, so we're not doing standard I/O file access. So very, very limited use of this C. So one of the big goals of an embedded C library is to get the heck out of the way, to remain small, tightly coded, and to not have a lot of dependencies. On a small system, I'm talking really small systems, this scale of board. That's about a 1 centimeter square board with just a processor chip and a couple of chips that are doing things. Small memory. In the modern era, embedded systems, RAM is much more constrained than ROM. The Sci-Fi board, this is a Hi-5 Rev B board. It has, a few kilobytes of ROM and, maybe 100 or 200 kilobytes of ROM and very little RAM. 2 or 3, maybe 16 kilobytes of RAM. So you want systems that have a very light RAM footprint, but also that don't use in a lot of the embedded work that I do in space applications, so satellites and rocketry stuff, those are very, very sensitive to failure modes. And so when I'm coding an application to run in a satellite, I don't want to use dynamic memory allocation at all. I want to statically allocate every possible object I will ever use in the lifetime of the application so that I know that there's absolutely no possibility of running out of heap. And so you want a C library that isn't dependent upon malloc and free. Oftentimes your embedded system has no way to recover from that. On a lot of embedded systems, on the Cortex-M series of ARM, on the smaller RISC-V boards, they have 32-bit floats, but they don't have any 64-bit floats. A 62-bit float takes a quarter the space of a 64-bit float. If it's going to do floating point at all, that it be very aware of the difference in cost between 32 and 64. Of course, a lot of them have none at all. Okay, so I've been doing embedded application development on 32-bit processors for about 10 years now. And I do all my stuff in free software. And when I started doing embedded development, I started working on 8-bit processors. When you get an 8-bit processor, like an 8051 or an AVR at Mega 328 or something, the development environments for those processors come with a C library. So SDCC comes with a C library. The AVR C compiler comes with AVR libc. So they all have a C library with them. So when I moved to 32-bit development for ARM, it's like, well, where's my C library? I'm sitting here coding with my happy little compiler. The compiler's provided. Where's strcpy? And the answer is crickets. There is no real standard C library for embedded systems in the 32-bit world. When you download the ARM compiler for 32-bit embedded development from ARM, it comes with NewLib, which is actually work done by Cygnus back in the 80s and 90s that was designed to provide POSIX-like environments on a wide variety of operating systems, including Windows and VMS and all kinds of stuff. And that NewLib source code base has been around for longer than most of us have been programming. Not as long as me, but so NewLib and NewLib Nano are designed for a real hosted or operating system rich environment. It has a library called libgloss that provides a POSIX API, and it expects underneath that for there to be a real operating system. So in a FreeBSD or Linux environment, libgloss could actually implement the syscall interface. I don't know if it does. I haven't looked at libgloss in a long time. In NewLib and NewLib Nano, these are applications that are expecting to, a library that's expecting to be supporting, real applications like a compiler, a text editor, and this kind of stuff where I/O operations need to be efficient and fast. So the standard I/O NewLib is very fast, but it's also resource intensive. You're running NewLib on a typical machine. Malloc is kind of expected. Most C applications written on big computers use a lot of dynamic memory allocation.
Hey, Mr. Freeman.
There are some proprietary options available. If you look around, if you do embedded ARM or RISC-V, or maybe even embedded power development, I don't know.
They were having some
there are commercially available embedded libraries for these proprietary systems that are supported. They're all closed source, of course. I believe, although I don't know because I haven't ever used them, I believe they probably come from the 8 and 16-bit world, so kind of migrating up the stack as the processors get bigger. So I can't fix them. I can't ship them with my GPL licensed code because they're closed source. So I can't actually use them myself. So that's what I found when I started doing development about 10 years ago. And it's like, well, what do I do? I used for a long time.
What are you doing?
I'm trying to remember the name of it. It was a BSD licensed, very small libc. I used it for so long, I don't even remember the name of it. There was another one. It was terrible. I wanted to get rid of it. So I decided what I really wanted to do was take NewLib and see if I couldn't take advantage of the fact that it had a bunch of really pretty good code in it. The math routines looked principled. They had error bounds documenting what they did. The string routines were optimized for a bunch of different architectures. It had a lot of good assembly code in it for making some of the low-level string operations go fast. It offered what looked like a very standards-compliant POSIX interface. So if you look at what a POSIX libc does, NewLib does a lot of that. It's been used by a lot of people for a long time, so the kind of little corner cases have probably been ironed out. And it's got all of that rich ANSI standards goodness that I wanted from the C library. If you're coding in a system, the last thing I really want to do is have to say, well, I know how this function is supposed to work in ANSI. Let me go see if my embedded closed source library does it the same way. Let me go dig through the documentation and diff the documentation against the real ANSI specification and see if there are differences. I really wasn't interested in that. I would like to be able to take my C development knowledge honed over the last 40 years and bring that into the embedded world. So one of the things that I looked at first was getting rid of this API wrapper that mapped a POSIX API onto some other operating system. Because in my world, there is no operating system. I don't have a file system typically. I don't have processes or threads, or I often don't have a real-time clock, so I have no date functionality. So I decided to just discard libgloss and see what happened if I got rid of that. And so I created this thing called PicoLibc.
We just sent the sample
it
down
takes
to
mostly
the
code from NewLib and
anti-mass
actually lives in the same source code
105%
format as
gamble,
NewLib
but we need
for
the
reasons we'll get into
resolution.
later.
The
It takes all of the
administrator is
math
very
functions,
concerned
the
that we get a
internationalization
conclusive
function, the
analysis of
string
today's
functions,
sample. I gather
with
they
all
went to
that
some lengths to get
performance and
it.
broad support and standards
waiting
conformance.
for you, Gordon,
But it discards
test
that
chamber.
ultra efficient and memory intensive standard I/O stuff. And I actually took the standard I/O code out of the AVR libc. Now this is an 8-bit libc. The standard I/O library for that was extremely well and tightly crafted. and it used essentially no memory. I'll go into what that looks like in a while, but in particular, a file struct, which is kind of the primitive object that you use to do I/O and standard
I'm
I/O,
afraid
takes
we'll
just
be
20 bytes
deviating
of
a
RAM.
bit from standard
In
analysis
newlib,
procedures
file
today,
struct would take
Gordon.
about
Yes,
7
but-
or 8 kilobytes of RAM with buffering and all this extra data structures that it had. So I'm saving an enormous amount of RAM. Now, obviously, when
With
you
good
get rid of
reason.
buffering,
This is a
there are
rare
performance
opportunity for
impacts.
us. This
But
is
in
the
my
purest
applications,
sample we've seen
that's
yet.
really not a big deal.
And potentially the most
Now, I say it's
unstable.
adapted
If you
from
follow
the
standard
AVR
insertion
libc. It's not
procedures,
exactly the
everything will
same
be
because the
fine.
AVR
How
libc had a
you can
bunch
say that,
of 8-bit
although I will admit that the
Atmel
possibility of
assembly
a
code
resonance
doing some of the
cascade
low-level
scenario is
things like
extremely
formatting
unlikely.
floating point numbers.
I remain
So I actually had to
uncomfortable
replace
with
that
this.
with some
Gordon
C code.
doesn't need
I
to
think
hear
I
all
found
this. He's
pieces
a highly
on the
trained
web
professional.
that was appropriately
We've
licensed,
assured the administrator
and
that nothing
incorporated that
will
in
go
and then did a
wrong.
bunch of other stuff on my
Yes,
own.
you're right.
Here's
Gordon,
what
we have
standard I/O
complete
looks like
confidence
in
in you.
Well,
PicoLibc.
go ahead. Let's let him in.
This is the entire structure. There's no pointers here except to functions. It's got a single character unget buffer, which is all that ANSI requires. So if you try to back up your input more than one character, sorry. Applications should be certainly well crafted to avoid that. Yeah, I actually had to, for one application of this, I actually had to put another layer of unget on top of that because I needed 3 characters of unget. Some flags to define the characteristics of it. And then basically 3 function pointers. And the 3 function pointers are put a character, get a character, and flush the output buffer. The original AVR libc didn't even have flush. It really expected that put a character to go right to some UART or something. But because I'm using oftentimes machines with USB interfaces, I need some way to say, okay, actually signal the host that you have data that's ready for transmission. So I needed a flush function. And that's basically hooked directly to flush. So if you call flush, you end up calling that function pretty directly.
Stage 2 emitters
So
activating now.
the PicoLibc then puts underneath this,
Gordon,
if
we
you happen to
cannot
have some
predict
which
how long
implements
the system can
a
operate at this level,
POSIX
nor
syscall
how long
interface,
reading will take place.
there's
Work
a
as
layer
quickly
you
as
can
you
add
can.
underneath PicoLibc that takes
Overhead
advantage of
capacitors
read-write,
to,
LC open and close, so the only 5
105%.
functions that it needs. Did I count that?
It's
The only
probably
5
not a
functions
problem.
that it needs, and then it
But
provides
I'm
open
showing a
FD
small
open and all those
discrepancy. Well,
on top
no,
of that.
it's well within acceptable.
And layering with
Sustaining
the
sequence.
same struct file. So you can get buffered I/O underneath PicoLibc.
I've just been informed that the sample is ready, Gordon. It should be coming up to you any moment now.
Okay,
Look to the
printf and
delivery
scanf.
system
The
for your
dominant
specimen.
use in my world of embedded programming, printf and scanf, is pretty darn simple. I use printf and scanf for debugging, because in the embedded world, debugging printf is an awesome tool, just like in Linux, right? I also use GDB. Don't get me wrong. Printf is not the only debugging tool that I use. So one of the problems that obviously that printf and scanf has is that they, in the ANSI spec, they support floating point input and output, right? You expect to be able to read and write floating point numbers with printf and scanf. But that means that if you use a version of printf and scanf that supports floating point input and output, it's going to pull in all of this floating point support. If you have a processor that doesn't have an FPU, you're going to suck in all the soft float code out of your kernel, out of your libgcc. So what I've done is I offer int only and float only options, which are available as a compile time option for your application. The library actually expresses all 3 versions, and you can select on a call-by-call basis whether you're calling one that only handles integers, one that only handles single precision floats, or one that handles integers, single precision, and double precision floats. And you just define these anywhere you like before you include standard io.h. And it will redefine printf as __i_printf to say this integer only version, or __f_printf to say that it's a float only version.
Gordon, get away from
And that saves an enormous amount of memory.
Shutting down?
Networks.
No.
So to
Attempting
use
shutdown?
float only printf.
It's not.
How many of you are
It's not shutting down. It's not.
C's awesome ABI for floating point numbers? Yeah, well, I'll explain it briefly. In the C ABI, because of its origins on the PDP-11, I'm pretty sure, I'm pretty sure that's the reason for it. When you pass a float, which is to say a 32-bit IEEE 754 number, to a function, the compiler helpfully coerces that to a double 64-bit value before it passes it to a function like printf, which takes untyped or var args parameters. So kind of the default type for a floating point number being passed to a C function is a double in the case of printf. So if you want to pass just a float and not a double, you have to do some ugly magic, and I did it with the usual collection of C inlines. This is not a macro, actually. Printf float does something horrible. It takes a float, sticks it in a union with a 32-bit int, passes the 32-bit. And when I figured that out, I was like, well, that's really awful, but that's going to save me a lot of space in my executable. Okay, here we go.
Thank God for that
sometimes C
hazard
is not my favorite
I'm
language.
afraid to move him, and all our phones are out. Please.
Okay, so that's what this does. The printf float macro, of course, if you don't define picolibc float printf scanf, the printf float macro just passes it as a double, because that's what it's expecting. And this is actually a program you can run. This is a complete picolibc program. We'll see this running in a little while. Okay, so what does this do for the size of my executable? Here are the three different versions. The integer-only version, the version with floats, and the version with floats and doubles. Now this is on a RBC2 IMAC processor, which is a RISC-V processor that includes integers, multiply, atomics, and compressed instructions. But it does not include floating point or double precision hardware. So this is pulling in that soft code library. You can see the impact of that. So the integer-only version is 2 kilobytes. The float-only version, which is the one that doesn't have double, is 8 kilobytes. But when you have to pull in 64-bit float emulation, you get almost 13 kilobytes of code. So you can see by just getting from double to float, I've saved 4 kilobytes of space, which is, in my world, that's a lot. So it's pretty valuable. Also runs
Alyx?
faster because now I'm
Alyx,
only
you still
doing
there?
computations on 32-bit instead of 64-bit values. Okay, another adventure that I had. NewLib comes with kind of the oldest style of thread local storage I can ever possibly imagine. NewLib actually has a structure in the library that defines every single possible global state used anywhere in the library in a single structure, with pointers and all kinds of magic, and sticks it in this structure so that if you use any thread local variables in NewLib, you end up allocating one of these structures for every possible thread local variable in the entire library. So the structure can be huge. In particular, it has standard I/O buffers in it. Yay! It has things like big num values for big num buffers for floating point to string conversion functions. It has everything. It's an enormous structure. I really didn't like that structure, and the worst attribute, of course, is that it doesn't have any real native support for defining how that structure is made thread local. Now, in my old world of just using derpy little ARM embedded processors, there was only one core. So you could use a global variable to point to the shared global area, and when you switched threads, you would change the global variable. In my RISC-V world, I have a lot of deeply embedded processors that have multiple cores. So you can't use any in-memory state to reference the thread local state. The only way that I could do that is by using the RISC-V TLS support, which dedicates a register in the processor, the thread pointer register, to reference this thread local storage. So I could have used the NewLib giant global data structure and pointed my thread local pointer at that, but now my application can't use any thread local storage because NewLib takes it over, right? Because I only have one pointer. So what I did instead is like, okay, I'm just starting from scratch. I'm going to say, am I standing in the wrong place? Okay. Okay, awesome. So instead what I did is I said, okay, I'm going to actually use TLS storage and convert the entire library from using this global data structure to using TLS structures, to using TLS variables. The awesome part is on RISC-V, TLS support is fantastic. There's a dedicated register name in the ISA. called the thread pointer that points to your TLS values. So when you fetch and when you load and store TLS variables on RISC-V, you're using a register and an offset, which is actually more efficient than using a global variable, because the global variable has to have an address stored in memory that you fetch and then load again. So it turns out that TLS support is actually better than global variables on RISC-V. This is not true on some other architectures. Some of them don't even have a register in the processor at all to store in a typical embedded environment. And so you're back to using a global variable, which is fetched through a function call. So on ARM, alas, every time you make a reference to a TLS variable, you make a function call to get the TLS pointer, which is fetched out of memory, and then you use an index off of that. Okay, so I added a few APIs to the library so that an RTOS sitting on top of picolibc or using picolibc could poke picolibc and allocate TLS block for each thread that it allocated, initialize it with the constant data, and do all of that stuff. But the awesome part is that by arranging the linker script in a magic way, I could get the 0 data and initialized TLS data initialized automatically by the application at startup time with 0 overhead. I had to assign the thread pointer register to the correct value. So that was kind of a neat hack. The linker scripts do that for you. So if you use picolibc and you enable threading, then you're going to need to go look at the linker scripts that come with picolibc to figure out the magic to get the thread local storage stuff initialized. Of course, TLS is optional. Right now in the Debian build, the embedded ARM compiler TLS is disabled, so you don't have TLS in the ARM world, so you don't have that performance cost. Okay, the other thing I wanted to be able to do is I wanted to be able to build applications that I could run under QEMU, or I could build simple applications to run on an existing system. So I kind of wanted a complete library. I didn't want something that I had to build. I had to build my own startup code. I had to write my own linker script. I had to do all of this work on my own just to get an application to run, which is what I experienced when I came to ARM 32-bit embedded development. So I wanted to provide the C runtime to start up picolibc and a linker script. Now, of course, when you get into embedded development, eventually whatever I provide is not going to be sufficient. But at least it provides you a starting point of understanding what you need to do. And it may provide some useful hooks, and it certainly provides for me an ability to run applications in picolibc under QEMU, which is really useful for testing. Let's see. Okay, another really useful tool for debugging in embedded environments is something called semi-hosting. How many of you have used semi-hosting in the ARM environment or other environments like that? Cool. So I'll explain what it is briefly, because it's kind of cool. So when you're running under QEMU, you actually have a real operating system several layers down in the emulation stack. So it's kind of the easiest one to explain. So what semi-hosting does is it provides a way for the application running in the emulator to signal the emulator that it wants to do something in the operating system that the emulator is running on. Similarly, if you're running an application on a host and are using GDB to that application over a link, semi-hosting allows the application running on the actual target to signal GDB over the debugging link that it wants to talk to the operating system that GDB is running on. And one of the things that I really wish I had known that I could do when I was developing USB drivers was to be able to do debugging printf using semi-hosting out to GDB. Because the way I typically ended up doing debugging of USB drivers, because before I had USB running, I had no way to print anything for my application. So it would have been awesome if I had known about this technique. So this is fantastic. The semi-hosting that ARM does is also supported by RISC-V. So they have basically the same semi-hosting support. It does console and file I/O, and it does one more amazing function when you're running on QEMU. You can call exit. So when you call exit in your, so I've got a board sitting right here, right? It's running some embedded application. What happens when I call exit on this board? What does it do? Typically, exit is a no-op. It'll simply just return, and your application keeps going. In the best of all possible cases, exit will spin forever. But it doesn't. It certainly doesn't tell you if that application got to exit or print an error, a status return, or anything useful like that. But in semi-hosting, what you can do is you can actually get the exit code, which is just a magic number past exit, all the way back out to your hosted environment. And so you can detect if your application running under emulation, what exit code it's provided. So that actually turns out to be almost the most important part of semi-hosting. Can I get a number for my application, please? So the RISC-V QEMU patches are awaiting merge. I was waiting for the 4.2 merge window, and now some other helpful QEMU developers have suggested that maybe I just start poking on a regular basis to see if they would get my patches merged. They have been fantastic, the QEMU developers. I actually posted the first patch that I posted to do half of the changes. They completely rewrote so that they would actually work. Which was awesome. It's like, I had this really crazy idea. This does what I need for me. And the QEMU developer's like, there are problems with your code. You clearly don't understand how QEMU works. And it's like, you're right. So if you ever get a chance to interact with the QEMU developers, I highly recommend it. They were awesome people to play with. Let's see, so the RISC-V QEMU patches are awaiting. Obviously, they're in my GitHub and my personal Git repositories. So if you want to play with this stuff, you can today. They'll probably be in QEMU 4.3. I don't know if it's 4.3 or 5.0. There's great. Yeah, OK. Apparently, the decision has been made. I'm not watching that closely. OK. So I'm developing a libc. A libc has a long history of standard conformance and things that it probably should do. What's kind of a thing that you would expect a libc to have in it? Maybe a test suite, so that you could make sure that your library actually did what it promised. libc is actually a really, 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 really easy thing to test, right? It's got an API you call. It has a document that says what the API does, and it has a little specification that says this is what the result should be if this function is working correctly. So unlike a lot of places where I play, where testing is very difficult, libc is almost the easiest thing to test that I've ever played with. It turns out that newlib came with many, many, many tests. I think there's about 74,000 individual test cases, or test vectors, as they call them in the testing world. However, I'm reasonably sure they haven't been run in over 30 years. There's, as far as I can tell, no way to execute them in newlib, because newlib provides no way to construct an application inside of newlib that would actually run in an environment. It doesn't have any startup routines. It doesn't have any linker scripts. It doesn't have any QEMU support. It doesn't have any semi-hosting stuff. I don't know how you would run the tests for QEMU. So all the test vectors look pretty good. Some of them had rotted. There'd obviously been some automatic transformation of the tests that caused them most to fail. So I fixed all of the tests because I could actually execute them. I actually have the CRT, the startup stuff. I have the semi-hosting stuff. I can build applications because I have a linker script. So all of the tests now pass on RISC-V. They all pass on ARM. And they all pass on x86 and both 64-bit. So the library runs on all of those targets. It doesn't actually do anything interesting on x86, of course, because it's not really its target environment. But it's really a useful development environment for checking code because it's very easy to debug, and the compiling environment is much easier. The awesome part is the QEMU support for RISC-V lets you pick which architecture your processor supports, the emulated processor. RISC-V, if you were in the early parts of the session, RISC-V has like 8 different bits of possible support, whether it does integer embedded, whether it has a multiply instruction, whether it has atomics, whether it does compressed instruction mode, whether it has floating point, whether it has double support, whether it has hypervisor, whether it has vectors, whether it has bit operations. The standard tool chain that is included in Debian right now has 30 different combinations of these flags. And I really wanted to be able to test the picolibc compiled against all of these combinations, because a real silicon is very likely to be shipped in all these combinations. So I actually build picolibc 30 different times, I compile the tests 30 different times, and I run them under QEMU 30 different times with each of the target architectures. So I run 74,000 tests. I compile thousands of files in picolibc 30 different times, and I execute them all. Unfortunately, the ARM QEMU support is not so generous. In fact, the only embedded ARM that I could figure out how to get to run was the Cortex-M3, but I do run the tests under that. This, of course, does require the semi-hosting support, which is not yet upstream for RISC-V. So that will happen. That will happen soon. I'm obviously testing these locally on my own with my own QEMU before I release it. Here is actually a program that you can run with the distributed picolibc. This may be familiar to some of you. Yeah, so you can actually compile, execute, and run this. So if we had a little more time, I could show a demo, but I was spending too much time talking about, what? I got 5 minutes, awesome. So I want to show you actually how to compile this program. Here's the complete compile line. This is really long if you're used to reading the KNR book where it literally says cc hello.c. Yeah, I know it's a lot longer than that, but trust me, this is amazing, the fact that you can express this pretty concisely on a single command line. Now we're going to run the compiler, RISC-V 64 unknown ELF. GCC is the canonical name of the cross-compiling compiler for RISC-V processors. It's RISC-V 64 because the default architecture that it compiles for is 64 bits. But this compiler actually supports all possible RISC-V targets, 32 and 64 bits. Don't be confused. I provide a GCC specs file that modifies the compiler behavior to insert picolibc and all the other necessary flags, blah, blah, blah. Again, if you need to do this manually, you'll have to dig up the file and dig out all the bits you need, but it's certainly possible. Then I define the architecture of the target, which is, of course, the Hi5 Rev B board, which is an RB32 IMAC, 32-bit RISC-V with integers, multiply, atomics, and compressed instructions. The ABI is ILP32, which is to say integers, longs, and pointers are all 32 bits. And then I'm going to use this linker script, which I'll show you in the next slide, that defines the addresses for the application. I'm using this -- oslib equals semi-host, and that says that I have an operating system library that provides exit, putchar, and getchar, and it's the semi-hosting one. If you want to do a different OS lib that provides these things, totally possible. And the reason that it's a magic compile time thing is it has to be inserted on the compile line after libc. Normally, if you just put a library on this command line, it would be inserted before libc. So I've done this magic hack in the picolibc.specs that sticks this library, which is just libsemihost.a, it sticks it after libc. So that's why that's there. And then you just give it the name of the program, and it compiles it away. So in order to run on a particular target, you have to tell it where the memory of that target is. And this is that linker script, that hello world.ld script that I was talking about. It tells it where the flash on the target is, how much where the RAM is located, and how much of each there are. And that's all you have to do. And then you tell it, oh, and go use the script from picolibc that does all the magic to get TLS to work and does all the other initialization stuff. Okay, so how big is this application? Well, the awesome part is when you compile that, it's really, really tiny. Anybody know why this is smaller than my printf example before? Why is this only 894 bytes and the stupid printf example was 2 kilobytes? Why is that? Yes, exactly. The reason that this is smaller is because GCC says, oh, you called printf with a constant string. I can remove the new line from that and call the puts function. It's like, ah, oh, terrible. Yeah, whatever. But it is really, really small. If you did it without that optimization, of course, you would get about a 2 kilobyte executable. To run it, you can actually run this under QEMU, and all you have to do is, the usual. If any of you ever seen QEMU command lines, they all look like this. They're like 47 miles long with a million options. Yeah. This defines all the things in order to construct a virtual machine that can run that executable, and it runs it just fine. So, what? Okay, so I can actually run that as a demo here pretty easily. So let me. I'm just going to do this. I think it's probably easier. Okay. So as you can see, I have hello world.c. Oops. And of course, I have a makefile, because that's the kind of person I am. And this is going to compile all three versions, the integer version, the floating point version, and the full version. So if I just compile that, you can see those compile lines look the same as the ones that I showed you before. I think they should be the same. Oh, I'm emitting map files. I was doing some debugging, so I had hacked up the makefile recently. Trying to figure out why. I think I had made some mistake somewhere in picolibc. I was trying to figure out why I was pulling in some double precision code in the float version. It's a pretty common problem. You don't notice that except that the size explodes by another 8 kilobytes or so. Okay, so now I can actually run this. And this has that, a million options setting up for QEMU, and it's going to execute the QEMU with all those options. It prints out hello world. It's actually. And if you actually run this, just the integer version, it actually says, oh, by the way, you passed me a floating point format character. I got no support for that. So it says star float star. So you can actually tell that it's different. So that is my talk about picolibc. Thank you all very much for attending. I have a minute or two for questions, you say? He was letting me have a couple of questions. The question here.
So obviously you're aiming at tiny embedded systems. Can you build this on like a normal POSIX space, so you could prototype on that and then before putting it on?
Yes, and in fact, that's how I do most of the development for picolibc. As I said, I have, so the awesome part is if you link with picolibc and compile against the picolibc headers, you can still also link against glibc, and it's going to hit all of the syscalls in glibc. So when I talked about that emulation layer that lets you call read, write, open, close, fseek, those functions are available in glibc with the correct function signature. So you can compile your program against picolibc and glibc. It will use the syscall interface from glibc and use the rest of the library from picolibc, and so you can do all of the testing there. And that's in fact how I've done most of the conformance testing for this, is in that environment before I got the semi-hosting working. Yeah, it's a very useful development environment. And that's something that newlib, I discovered, I tried to figure out how to get the testing stuff working in newlib, and so I compiled newlib as a native library and said, don't do cross compilation for newlib, and I typed make, and it said $, the shell prompt. It literally did nothing. It's like, we don't need a C library on your system. You already have one. So I can't do that with newlib because the build system doesn't allow that particular case. One of the things I didn't talk about in newlib is that in picolibc is that it actually replaced the entire build system with Meson, which has been a fun adventure and something I should talk about some other day. Other questions? Ben, did you have a question?
So there is this incestuous relationship between GCC and glibc that you're building GCC against when you want to do a proper full user space
yes.
in GCC. Are you completely avoiding that, or you also have that possibility?
When I build the cross compilers for ARM and RISC-V on Debian, I do not reference newlib. GCC is built without reference to a C library there. The only reference you need to a C library when building GCC is for libstdid C++. That is the only reason you need a C library. My plan right now, in order to support C++ and RISC-V embedded environments, is to pull that library effectively out of GCC and compile it against each libc separately and package it as a separate library.
Because I do remember hitting some issue around TLS as well. There was some, at least on PowerPC, some issue about the stack protector constant being at a fixed offset from the TLS defined by the C library.
That might be a PowerPC thing. Fortunately, because on RISC-V, ARM, and x86, the TLS stuff is not referenced to the stack at all. It's a separate pointer.
No, not TLS itself. The stack protector constants.
Oh, stack protector?
Yeah.
Protector. No, so I haven't seen any particular trouble with that. I actually am not building. I actually have a GCC hack to disable the need for a libc when building GCC.
Thank you for the talk, very interesting. You mentioned developing USB stacks. I think in something like this, if you're doing standard I/O against something in an embedded environment, you probably then have some SoC specific driver for speaking to a UART, for example.
Yep.
The USB case is not quite so simple. You have this whole protocol stack, which at least some of it is perhaps hardware independent. Do you think something like that belongs in an RTOS or in a vendor-provided sort of hardware abstraction library, or is that something that really you should have in a standard library, if not, albeit not a C standard library? But
That's a good question. So I mean, embedded system development has that perpetual issue. Where do you put code, right? In my environment, typically, the USB stack, sometimes I let the USB stack be provided by the chip vendor. So in the ESP32 work that I've done, I'm using the USB stack provided by the vendor. For Atmega 32U4, I wrote a USB stack because I needed one small enough. And so I have that myself, and it provides the interfaces that PicoLibC requires. So that's in my application, outside of the PicoLibC or the vendor-provided environment. So yeah, I mean, obviously there's a lot of code that could be shared, and probably should be shared. But one of the challenges of embedded development is that the problem with sharing code. Yep. The problem with sharing code is that shared code is often larger code. Shared code often provides more functionality than you need. And so often, it's obviously a trade-off. Not related to PicoLibC, just kind of the overall embedded development environment. But yeah. Okay, I think with that, we're going to end it and go on to our next speaker. Thank you very much for your time today.
Face from where you are. I'm a research engineer. I work with the Trustworthy Systems group at CSIRO's Data61, and I'm part of the team that develops the SEL4 microkernel. And in my spare time, I like to write a lot of Rust. In this talk, hopefully by the end of it, you'll have some idea how the concept of write once, run anywhere is possible, and how a programming language's runtime interacts with its build system and the operating system in which it runs in order to provide a portable interface to satisfy that guarantee. And how when you change what the operating system is able to provide, that affects the ability of the language to provide that guarantee. A brief overview of how we're going to get through all of that. I'll start with what is a runtime, look at how runtimes let us develop software for major operating systems, and then we'll strip away the operating system and slowly build it back up on top of a microkernel to get an understanding of the scale at which a language can provide us with these portable tools, up to the point where we can write user applications again. And then I'll briefly mention the work I've done with Trustworthy Systems that got me into this mess to begin with. So what is a runtime, or a programming language runtime? It is a component of the programming language toolchain, and it executes within the application. So for the purpose of this talk, I'm referring to everything that the programming language toolchain provides that is executing at the same time the application is. This can include components of the standard library or a monolithic runtime application itself. And these together work to provide a high-level interface that is consistent to applications programmed to it, that doesn't change as you move between platforms. Some features that runtimes tend to provide: process entry and exit is the most fundamental thing that your runtime is going to handle for you and abstract for you. Runtimes will provide dynamic memory management capabilities. This can be via explicit mechanisms like malloc and free, and it can also be via more managed systems such as garbage collection. Your runtime will often provide multitasking primitives for you. This can be abstractions on threading mechanisms provided by your operating system, but can also be mechanisms that perform multitasking within the application itself before handing off anything to the operating system for blocking and synchronization. Your runtime may abstract over the concepts of process management, how you start new processes and communicate with them, and in general, communication between processes and threads, and synchronizing them over a scheduler. More broadly, your runtime will give you mechanisms to interact with the file system, open files, close files, write and read data, use them as communication between processes or use them as persistent storage. Networking as well, communicating with other computers via a network, remote hosts, and a bunch of OS-independent utilities, string manipulation, arithmetic, maths. Often there'll be some kind of user interface. Usually this is just going to be the assumption that you can interact over a text interface via standard in and standard out. Sometimes your runtime knows enough about the system to provide you tools to set up graphical interfaces. There are three main ways that a runtime is able to provide these features to you. The first is via the tool chain. So as the application is being built, things can be analyzed, your code could be analyzed, or we could find files in the file system and embed those into the runtime itself to provide features. When the application is running, we can communicate with the operating system and offload the need to do work to that operating system. This can be things like process metadata about what the current process that's running, communication with other processes, and communication with services offered by the operating system. And then finally, there's just everything that the execution of the runtime is able to do itself. It can do work when called into explicitly by the application. It does work before and after main, process entry and exit. And if you have a higher level language that's running in an interpreter or a bytecode VM, it's able to perform a lot of work in the process of executing that application. Most of what I'm going to talk about today is this middle category, the operating system, and how we can offload work to that. To begin with, I'm going to give an example of what it's like to develop for a major operating system. In this case, I'm going to look at writing a Rust application to run on Linux. And in this case, our Rust runtime is able to handle process and entry and exit for us. It can provide us dynamic memory management primitives. We can do multitasking. In this case, Rust can provide us with runtime level multitasking, but we'll be looking at threading provided by Linux. A user interface in this case would be standard in and standard out should we use it. We can start new processes and communicate them using the command API. The file system, we can open files, create files. We can open network sockets using an interface in the standard library for creating network socket listeners and connecting to other computers. This is a simple file server that I've written in 2 functions, which should demonstrate some of the features of the Rust runtime. This is our main function. The first thing it's going to do is handle process entry for us. It takes the mechanism Linux provides for starting a process and uses that to initialize itself and then call this main function, which we've defined. And in this case, it's also going to handle any errors for us. If our program hits upon any errors, we're immediately going to return to the runtime. It's going to print a message and then exit. The first thing we're going to do is bind to a network address using a mechanism from the standard library for creating a TCP listener. And then we're going to listen to every new connection that comes into this network address and handle it. We're going to spawn a thread dedicated to handling each new connection. That thread is going to handle the request, throw away any errors, and then try and shut down the stream gracefully to close the connection. And then in our handle function, which is called in this new thread, it's going to start reading information from this network stream. It's going to read in a string, convert it to a path, validate that path, make sure it's correctly formatted. It'll check that the location of that file is somewhere in the subdirectory of the current location that this program is executing. We'll then open that file and then just read the contents of that file out to the network. The easiest way to look at what mechanisms the runtime is providing to us here is to look at all of these imports. So our first line is networking, the networking module, which gives us our TCP listener to wait for requests and listen to them. And then the mechanisms to communicate via that TCP stream. Our second line is multi-threading. This is an abstraction over the threading mechanisms provided by Linux. I/O is a set of standardized interfaces for describing what an implementer would need to provide to allow us to communicate using bytes. This could be to files, to strings, to buffers, to network streams. We have an abstraction over path resolution through the path APIs here. And this generalizes the different ways in which operating systems handle paths. We have the process environment here where we try and determine which directory in the file system our process is executing in. And we have the ability to open files and read files. And this last line here is just a type alias to tidy up the error handling in Rust to make the program nice and compact. But with these few lines, we have a basic file server that not only runs on Linux, but it will run on most major OSs without any change to this code. So it'll run on Linux, Windows, Mac OS, FreeBSD, and I don't need to change anything that is written here. And this is pretty representative of a lot of application-level programming across these operating systems. It doesn't do any graphical interface stuff. It's not web applications, but it covers most of the other cases. But what happens when we take away the operating system and we now have to interact directly with the hardware? What are we able to rely on? If we have a portable language, what is that language actually able to supply to us? I'm going to take the example of freestanding C on top of this x86 platform. And I'm going to talk about the most general form of runtime we could probably provide here that assumes the least amount of about the hardware case possible. So it's going to need to handle process entry and exit for us. Our process needs to start somehow. It could implement some sort of dynamic memory management. It could have a statically mapped region for the heap. It could provide some multitasking primitives, but any mechanisms for blocking or waiting on signals and resuming tasks is going to be largely provided by the application. Communicating with the user is quite difficult at this point. There's a lot of ways it could be done. We could make assumptions about the serial interface and use that, but that would be baking a lot of stuff into our runtime. There's no concept of processes here. There's no file system here to interact with. And there's no network driver for us to assume exists so that we create network connections. And the C standard specification doesn't even provide a networking API. For that, you need like POSIX. So this is pretty minimal. Our application from before, clearly we couldn't just run it here. It would need a lot more work to provide features to this runtime. And we would need to be doing a lot more work within the application. So the next easiest step to take to provide just that little bit more abstraction is our microkernel. And to cover just what exactly a microkernel is, I think this quote from Jochen Lidtke, I hope I've pronounced that correctly, sums it up really nicely, in that a concept is tolerated inside the microkernel only if moving it outside the kernel, i.e. permitting convening implementations, would prevent the implementations of the system's required functionality. If I can take a component of my kernel and move it outside of that kernel as a user application, and I'm still able to construct the same system I could before, there's no reason that should be in the kernel. So our kernel has the most minimal responsibility. We implement all of our system services outside the kernel as user applications. We have very small modular components that can be independently worked on and communicate over well-defined interfaces. And we also end up with a very small, trusted computing base. If I have an application that needs to, for example, communicate over a network, and it communicates with the networking component of the system, and that networking component doesn't depend on the file system component, then my application doesn't need to trust at all that the file system component is functional, that it's available, that it's implemented correctly, that it's not malicious. There's no dependency there. The microkernel I'm going to use today to describe things is SEL4, because that's what I'm familiar with, that's what I work on. And this is a brief description of some of the features that it provides for us. But primarily, SEL4 is there to guarantee isolation between user mode processes and to provide the mechanism for us to control how those can communicate with each other and how they are scheduled and the resources that they can access. But importantly, the kernel itself in this case isn't providing any policy as to how that is done. We use mechanisms to inform the kernel about what that policy should be. We've also formally verified it. The concepts that SEL4 has, firstly, is virtual address spaces. I can create a virtual address space. I can map in physical memory and device memory into any virtual address space for a user process. I can schedule threads that execute within that virtual address space. I can perform IPC and synchronization between threads executing in the same or different virtual address spaces. We have two mechanisms for this: endpoints for synchronous communication, notification objects for asynchronous communication. And then we also have some mechanisms for device I/O, IRQs, I/O ports. Tends to get a bit platform specific at that point. And then the policy for who has access to these objects and these resources and who can pass around access to these resources is encoded using capability objects and capabilities within CNode objects. But if this is the set of features that our SCL4 kernel provides to us, and we want
everyone. My name is Deb Goodkin. I'm the executive director of the FreeBSD Foundation. And I'll talk a little bit about the foundation later on, but I'm here to give you an overview of FreeBSD to start off our day. So the goals of today's, my goals for my talk is really to share our history, talk about why people and organizations use FreeBSD, and then also hopefully at the end or near the end I've convinced you to try FreeBSD and hopefully contribute back to the project. We're also going to talk about some of the features in FreeBSD, and I'm actually going to hand that part off to Philip, who he's an actual developer, and so he can cover those features a little bit more detail. So I guess I'm going to just go back here really quick. And the reason, and so I'll just give you a little bit about my background. I've been running the foundation for 14 years now. We're actually celebrating our 20th anniversary this year. And FreeBSD is going to celebrate its 27th anniversary this year, so to give you an idea of the history. And my background is where I was a low-level firmware engineer for many years in storage, and so operating systems, that's not my background, and so, but running the foundation for so many years, over the years, I'm learning more about it. And so I do have a goal this year that I just bought a new ThinkPad, and I've loaded FreeBSD on it. I actually have FreeBSD on my computer here too. But my goal is to be able to use that as much as I can. And I mean, really, my goal is to use 100% of to be able to run the foundation 100% using my FreeBSD system. So that's the goal. And so at the next conference, I'm hoping to have that system used to run my presentation on. Oh, and part of logistics too. So we do have some swag in the back. I didn't really have a place I could put it. So on one of the chairs back there where Matt is sitting as his warm up. So we do have some pens and lots of stickers. So please feel free to take that video. So the FreeBSD world, this is sort of how we picture it. And you have three different components. And so one, on the top right is the actual operating system. So that's what you download onto your computer. That's what I'm running in VirtualBox here. And that's what FreeBSD is, it's actual code. In the middle, that's the project. And the project is made up of a community of thousands of people who contribute code, they contribute documentation, they contribute in various ways to the project. That is the project to FreeBSD. And then the last component is the FreeBSD Foundation, and that's what I run. And we are, so in the United States, so we are based in the US, and we're considered 501c3. You may not be familiar with that. That's how our government sort of categorizes us, and it means that we're for the public good. And so we 100% focus on supporting the project, and basically whatever the project needs, if it's a critical need, then we can help them in those areas. So what is FreeBSD? So I know there was at least one hand that was raised, a legitimate hand that was raised that wasn't familiar with FreeBSD. So first, I always like to use this, and I know it's not very nice to text because we're really not anti-text, but But people who don't know FreeBSD or they're not familiar with it, or they think like, oh, I know, I've heard it. It's a Linux distribution, right? And so it's always the first thing I try to tell people is it's not. And so I want people to understand that part of it. It is one of the oldest, largest, most successful open source projects around. It's a complete operating system. So when you think of Linux, Linux is the kernel, and then you have all these distributions, and to add the tools and userland. And so, but FreeBSD is all of that together. And I'm going to guess this number has probably increased, but it supports over 33,000 third-party software packages that you can run on it. To continue, it's created by a very technical group of people, and actually people who worked on the original BSD. We still have some of those people there too, who are very involved in the project, which is really cool. It works on many different platforms.
shot his wife. His son came to investigate the commotion. The father shot him too. 204-863. His 6-year-old daughter had the good sense to hide in the bathroom, but reports suggest he lured her out by telling her it was just a game. The girl was found shot once in the chest from point-blank range. The mother, who was shot in the stomach, after neighbors called 911, found the father in his car listening to the radio. As the congressional debate over gun control flares up yet again, we regret to report the murder of a wife and her 2 children by their husband and father. The father purchased the rifle used in the crime at his local gun store 2 days earlier. This brutal killing took place while the family was gathered at home on a Sunday afternoon.
Don't touch that dial now. We're just getting started.
Retrieved the rifle and shot his wife as he was the son came to investigate the commotion. The father shot him too. 204-863. His 6-year-old daughter had the good sense to hide in the bathroom, but reports suggest he lured her out by telling her it was just a game. The girl was found shot once in the chest from point-blank range. The mother, who was shot in the stomach, after neighbors called 911, found the father in his car listening to the radio. As the congressional debate over gun control flares up again, we regret to report the murder of a wife and her 2 children by their husband and father. The father purchased the rifle used in the crime at his local gun store 2 days earlier. This brutal killing took place while the family was gathered at home on a Sunday afternoon. After killing his family, the father hung himself with a garden hose they had in the garage. After killing his family, the father hung himself with a garden hose they had in the garage. After killing his family, the father hung himself with a garden hose he had in the garage. After killing his family, the father hung himself with a garden hose he had in the garage.
Låt dina öron lyssna till radio. Hör din röst. Kan du höra din egen själs skrik? Låt oss välja. Min röst som förtäller framtiden eller dina plågade. Någon på väg. Du kan välja. Ditt liv. Din framtid. Låt som du är. Så kanske du redan upptäckte. Ja, radiodramat får 75 år för att vara sanning. De är här på och de övervakar och ser allt. Lita ej på mig. Lita ej på polisen. De är redan kontrollerade av dem. Så har det varit i 75 år. Endast vår bästa kan hålla. Du har en rätt att bli en av oss. Så välkommen till vår. Mycket snart av transporterna till en ny dimension.
I'd never survive a jump from this height.
No, absolutely not. Why? Were you considering it? Alyx? Alyx?
Jump from this height.
No, absolutely not. Why? Were you considering it? Alyx? Alyx!
Okay, Alyx, we need to find that battery. The radar is showing that it's around here somewhere. I just don't know where exactly, but that's why you're here, right? Alyx, the thing's getting out. I'm having a signal interruption. Just trying to get through this cab. There'll be something.
Last 4 cells. Last one.
platforms, and there's millions of deployments out there. So this is my simplified version of where FreeBSD came from. And so you may have heard of Unix coming from AT&T. They actually celebrated their 50th anniversary last year. I think it was in November, and so that was really exciting. It went to Berkeley, and they were doing research with it. Some people refer to it as Berkeley research. Oh gosh, the term slipped my mind, but BSD is Berkeley Software Distribution. But it's also a research Unix version. And then in the early 90s, it split off into NetBSD and FreeBSD. So this is this timeline that we created. That's actually, it scrolls, and I use it just to show how Unix started in '69, and C language was there at Bell Labs, and just sort of to show you the history of how it went to Berkeley in '74, and you may have heard of names like Bill Joy, and if you haven't, he's one of the co-founders, the son. And so he took over, he was basically the primary developer of the 386 BSD.